Okay, as I mentioned, we're switching to collisionless shocks now. Now we're very happy to have Victor Zhang from LLE, who will be talking about magnetized collisionless shocks in the universe and the laboratory.
All right, okay. Thanks, Will. Thanks for having me, and thank you all for coming here. So now we are switching gear a little bit to shocks. I am excited to share with you about some of my research in the past few years during my PhD. So I'm Victor from the Laboratory for Laser Energetics, University of Rochester. So we have been doing some interesting stuff on magnetized collisionless shocks related to astro and the lab astro. I don't need to explain to you guys what a shock is, what makes it magnetized or collisionless. So let's jump right into the topic. So here is my summary slide. We did some kinetic particle cell simulations on shocks, including quasi-perpendicular shocks and quasi-parallel shocks. The angle we're discussing here is the angle between the B field and the shock normal direction. So, and this angle can change a lot of things with very, very different physical processes involved with shocks at different angles. So we have found that for perpendicular shocks, they can form quickly due to a modified two-stream instability. And because of this instability, these shocks are readily achievable at kiloJoule TeraWatt laser systems such as omega EP. For parallel shocks, we can achieve a early stage quasi-parallel shock on the National Ignition Facility, and Fermi accelerated ions are expected to be observable. And from this simulation, we observed anomalous electron heating due to an effective ion electron energy exchange. Then we spent some time trying to figure out this energy exchange mechanism. So we were lucky to find that this energy exchange can be reproduced by a counter-streaming system. And this energy exchange is achieved through resonances between electron Whistler wave and ion MHD wave. And it's finally achieved by Landau resonance. Teamwork makes the dream work. So I'd like to thank my wonderful collaborators from the Laser Lab, UCLA, Pacific Fusion, and Universidad Castilla-La Mancha. And of course, my funding agencies, NERSC and the Osiris Consortium. So like I said, I'm going to talk about three little things for this talk. So the first one is about quasi-perpendicular shocks. They are relatively easy to do. So the second one is about quasi-parallel shocks. They are much more difficult to achieve experimentally and also in the simulations. The third one is going to be about the energy exchange. It is a very interesting BS, basic science, I mean. So I have these little flags over here. You will see them a lot, and you can see what I'm talking about on my slides. Okay, so let's talk about perpendicular shocks. So a collisionless shock can be launched by a laser-driven piston. So we can do this with lasers on the left. This is our wonderful lab. So we have a couple of football field size laser systems. We have omega 60 on the right and over here omega 60, and we have omega EP here. In the middle, I'm showing you our experimental setup omega EP. So first, we have the hydrogen gas or neon gas can be injected from this gas jet system into a Taki chamber. And then the B field can be applied by the MyFates coils. And then this laser-driven piston can push the ambient gas and form a shock. So the B field is going into the page, and the shock is going to the left. So we have a perpendicular shock here. So in our simulations, instead of a moving piston, we have a reflecting wall or an ideal piston. So the plasma is drifting to the right, hits the wall and get reflected. So we will have a shock propagating to the left. So on this slide, I'm showing you the simulation result. So the plasma reflected off the wall or the ideal piston forms the shock very quickly. So precisely speaking, this shock can form within a tenth of an ion gyro period in hydrogen plasma. So here I'm plotting the 2D density profile and the y-averaged density and the B field profiles on the left. The plot on the right-hand side is the 1D density evolution. So we can see some reflected ions here in the upstream, and we can also see a shadow over here. So this reflected ion in the upstream indicate we have a supercritical shock. So the reason for that a perpendicular shock can form so fast is because of an instability called modified two-stream instability, or MTSI. So I have this ugly, beautiful equation here for the dispersion relation of MTSI. So we can numerically solve it. From this, the growth rate of MTSI is basically a function of sonic Mach number. A sonic Mach number larger than 3 should give us a good enough growth rate of MTSI for hydrogen. If you look at this right-hand side, you can see that growth rate of MTSI is much larger than the ion gyro frequency. So we should expect a fast shock formation time, much less than an ion gyro period. So I don't want to spend too much time on perpendicular shocks because we have more interesting things to come. But here I'm showing you a few proton radiographs from our omega EP experiments. So we did demonstrate the formation of a quasi-perpendicular shock, which is here. We have 3 shocks here. Okay, so here is the summary for the perpendicular shock. It can form quickly due to a modified two-stream instability, and they are readily achievable on laser systems, omega EP level laser systems. So now let's talk about parallel shocks. So why do we care about parallel shocks? Because they are believed to be one of the most efficient accelerators in the universe. So Fermi acceleration was first proposed in the 40s, and it was then developed into a diffusive shock acceleration, or DSA, in 70s. The basic idea of Fermi acceleration, or DSA, is the cosmic particles can gain energy from crossing the shock front many, many times, and eventually we should have a power law energy spectrum. So here I have a beautiful movie from NASA to show you the idea. So National Ignition Facility, which is the largest laser in the world, offers a unique platform for studying quasi-parallel shocks and shock-accelerated particles by providing a large magnetized uniform upstream and strongly driven flow. So we do need enough space and enough time to create a quasi-parallel shock. So the scale we talked about here are only achievable on the NIF. So as a result, quasi-parallel shocks have never been created in the lab before. On the right-hand side, I am comparing some key parameters between previous omega experiments and the ongoing NIF experiments. From here, especially I want to point you to look at this system size and system time. You can see that the NIF experiment is much larger than the omega experiment. So this is National Ignition Facility, a 3 football field size laser system with 192 powerful lasers. So we want to make the first ever observations of quasi-parallel magnetized shocks in the lab. In the middle, I'm showing you the schematic, the experimental setup on the NIF. So here we first have this gas pipe. We have hydrogen gas inside. So the B field is applied by the coils, and this X-rays from this laser target interaction will ionize this gas into plasma. And finally, we have this laser-driven piston. So we can have a shock going in the 30-degree angle. So we expect to see some accelerated ions in the direction of the B field. And our first shot day has been done last year, and the second shot day is scheduled next year. So here I'm showing you the movies of our quasi-parallel shock simulation with 3 different shock angles. I have 0 degree, 15 degree, and 30 degree here. So the good news is that our peak simulation confirms that quasi-parallel shock can be formed within the space and time given on the NIF. So from here you can see some difference between different shocks here. Apparently, shocks take take longer to form at smaller angle. Right. So I want to remind you that we do care about ion acceleration. So here I tracked some ions in the simulation. So from their trajectories, for example, here on the left in this xt plot, you can see these ions can cross the shock front many times, and they can get accelerated. So the white dashed line here is the shock front. The color here indicate the energy of the particles. On the right-hand side, I'm showing you the ion trajectory in the continuous 2D space. So this ion repetitive crossing of the shock front is observed, and the maximum energy of this ion can achieve is about 350 keV, which is about 35 times of the shock energy. That's quite impressive considering we are only simulating a short period of time. Okay, so in the simulations, we have observed anonymous collisionless electron heating. So we're talking about temperature. So when we talk about temperature, we have this Rankine-Hugoniot jump condition. So we should expect in the downstream, the temperature T plus Ti should be on the order of 3,700 eV. But this equation doesn't tell us about energy partition. What is the energy ratio between ions and electrons? So this is where simulation kick in. So here, from this energy spectra here in the downstream, the ion temperature at the end of the simulation, the ion temperature is about 2,000 eV. The electron temperature is about 1,500 eV. So we have a temperature ratio T over Ti is about 3/4. So we do have some collisionless electron heating here. So before we move on to energy exchange, so here is the summary of quasi-parallel shocks. So we can achieve a early stage quasi-parallel shock on the National Ignition Facility, and we expect to see Fermi accelerated particles from the experiment. And this quasi-parallel shock can efficiently heat electron due to some energy exchange we will talk about. Okay, so now let's talk about ion-electron energy exchange. So this energy, the energy partition in collisionless shocks has been a long-term open question. So if we assume independent thermalization of ions and electrons, we should expect T over Ti is on the order of ME of Mi, which is very, very small. But observations indicate that this ratio can be much larger here. So here in the middle, I'm showing you some observational data, T over Ti as a function of Arfanic Mach number. From here, you can see we have more electron heating at lower Mach numbers. So here on the right-hand side, I'm showing you another observational data from MMS. So here, T over Ti is about 0.3. So we do have electron heatings from observations. Okay. So explicit peak code without any approximations provide us a self-consistent way to study collisionless ion-electron energy exchange. So we built a simplified shock-free picture here to mimic the shock transition region where most of the heating happens. So it is very important to know that we do not want to simulate a full shock because we have already done that. And here we only consider a small part of the region that include in a full shock simulation that includes everything, it would be impossible to separate individual physical processes. So we are simplified. So we simplified this picture a little bit. So here we have counter-streaming ions in the electron raster frame, and we have this zero current condition, and the Coulomb collision module is turned off in the simulations. So I have the picture here. So the Mach number can change, the density ratio can change, the angle can change, and of course the temperature can change. So we can, from this picture here, can cover a good parameter range that we are interested in. Okay, so here I'm showing you an example of what this energy exchange look like. So here we have a symmetrical field parallel setup here to make it easier. So to see if we, here we want to see if we can reproduce this energy exchange. So the answer is yes. On the right-hand side, I'm showing you the velocity distribution functions of this ion 1 species and electron. So let's play the movie here. As the simulation goes, you can see ions and electrons are both heated. We do see some energy exchange between ions and electrons, which is good. So here, I just showed you velocity distribution functions. So here I'm showing you the energy spectra from the exact same simulation. From here, you can see at the end of the simulation, the ion temperature is about 2500 eV, and electron temperature is about 1200 eV. And now, if we turn off the B field for the simulation, this is what we have. You don't really see a big energy exchange, and electron temperature is much lower than the magnetized case. And now, if we tilt the B field angle a little bit to 30 degrees, we have something like this. So we have a similar final stage, but so the different color here indicate different time. So from here, you can see that at 30 degrees, things can happen faster. So now we can say this energy exchange mechanism is magnetized. We do need a magnetic field to make it happen. Okay, so now we need to quantify the process. So because of the largely non-Maxwellian ion distribution, so we define a electron heating rate here, to quantify this. So the definition is here, it's dE dt divided by the difference between the electron thermal energy and the balance energy. The balance energy here assumes thermal equilibrium or maximum entropy. So here on the right, I'm showing you the simulation result, electron heating rate from 3 simulations here. Oops. So you can see the magnetized case has a much larger electron heating rate than the all-magnetic case. So the all-magnetic case almost has very, very small electron heating rate. So this is the growth rate look like in the K-space from the peak simulations. So we have some modes here. So now we want to figure out what these modes are. So on the right-hand side, we built a multi-fluid model, try to understand which mode is which. So from here, you can see they agree with each other pretty well. We have 2 figure-of-8 modes, and we have a nearly perpendicular mode. So here is, we can put them together. So here I put the theoretical result as contours on top of the simulation result. So it looks pretty nice. So before we can explain what these modes are, so we need to go back a little bit and do a quick review of low frequency plasma waves. So here I'm plotting the dispersion relation in the low frequency regime. So we have a few branches here. So here we have electron Whistler wave. It asymptote to ion to electron gyro frequency. So we have a few more branches here. Now we want to zoom in a little bit to the low K, low frequency range. So still we have this electron Whistler wave here, and we have 2 magnetosonic waves, one is forward, one is backward, and we have 2 Arfin waves, one is forward, one is backward. Okay, so what if we have a non-zero ion drift? So all these MHD waves will co-drift with this non-zero ion drift. Still we have magnetosonic waves, and we have Arfin waves. So now we can try to understand what these modes are. So let's look at this 64-degree. So I have this ideal dispersion relation in this dashed lines here. We have electron whistle wave, we have two magnetosonic wave, we have two R-fin waves. If we put everything together, this is what real world look like. And now we have unstable modes. So with this multi-fluid model, we can know that this mode here comes from the resonance between electron whistle wave and the backward magnetosonic wave. And this branch here comes from the resonance between electron whistle wave and backward R-fin wave. So back to this plot here, the inner circle is a resonance between electron whistle wave and magnetosonic wave. The outer circle here is the electron whistle wave and R-fin wave. Okay, so now we know what these are, and we can do the same thing for the nearly perpendicular angle here. Now we are looking at 84-degree. So we can do the same thing, and up here, this upper part comes from ion 1. This lower part comes from ion 2. And this unstable mode here comes from the resonance between two backward magnetosonic waves. So yeah, we know that what that is. And this nearly perpendicular mode results from two backward magnetosonic waves. However, here I'm going to tell you that this nearly perpendicular mode may not drive a significant ion-electron energy exchange. So this is why. So let's go back to this electron heating rate. This blue curve here comes from the magnetized simulation. This yellow one here comes from the unmagnetized simulation. So we don't see effective electron heating in the unmagnetized simulation, even though a similar perpendicular mode is presented. So this unstable magnetosonic mode may not drive a significant energy exchange. Okay, so now we know about instability already, and but how does energy actually get transferred? So it turns out Landau is the boss behind the thing. So Landau resonance is a wave-particle interaction that operates near the phase space of the wave, the phase velocity of the wave. So I have a cartoon here to show you the idea. There's no need to explain more about Landau damping. Every single plasma textbook has it. But here, let's still look at 64-degree. So here I am showing you the energy gain as a function of particle velocity at 64-degree. Here I'm plotting ions. From here, you can see for those particles whose velocity is larger than the phase velocity of the wave, the energy gain is negative, meaning that they are giving their energy away to the wave. And for these particles whose velocity are smaller, the energy gain is positive, meaning that they are gaining energy from the wave. Here I plot the same thing for electron. It has a much larger range, but the similar thing happens. Faster electrons are giving their energy away, and slower electrons are getting energy from the wave. So this is the signature of Landau resonance. So now we can draw the energy pathway. So first we have this unstable drifting velocity distribution functions. And through the resonance between electron whistle wave and MHD waves, we have this instability or wave. And eventually we have Landau resonance who can achieve this energy transfer. We have ion and electron heating. So here I want to show you our new wave resonance picture can recover classic instabilities like right-hand instabilities and non-resonant instabilities or Bell instability. We can apply a parallel setup and we can apply a cold plasma approximation. So right-hand instability is actually the resonance between electron whistle wave and backward R-fin wave, and the non-resonant instability or Bell instability is the resonance between the electron whistle between the resonance is the resonance between electron whistle wave and the backward R-fin wave from ion 2. And our new picture here extends previously studied instabilities to more general and more complicated regimes. So speaking of complicated regimes, so here I'm showing you what if we have a 30-degree angle. So here is what the simulation look like. So here is what our theoretical result look like. So with the multi-fluid model, we can know which mode is which. So here we have more resonance here. More resonance are activated. It can be very complicated. Okay, so here I have the summary for the energy exchange. So it can be reproduced by the counter streaming system, and it is achieved by the resonance between electron whistle wave and magnetosonic wave. And finally, non-dot damping is making it happen. So here is my summary again, and that's all I got to say. And love to take questions from here. Thank you.